So, in the last few lectures we have been talking about the basic metrics, basic statistical metrics for analyzing large complex networks. So, and we have got introduced to different centrality measures, page rank, etc. In this set of lectures from now onwards, we will mostly talk about social network principles, and one of the first social network principles that we will discuss is called assortativity or homophily. So, the idea is somewhat like this, that given a social network, rich people always tend to make friendship with other rich people. So, this is the idea of homophily or assortativity. So, also in other words you can say that the like goes with the like. So, rich goes with the rich and possibly the poor goes with the poor. Okay. So, if you look into the slides, the first example that we have here is a friendship network from one of the US high schools, and what you see here, there are 3 different types of nodes in this network. So, the black ones correspond to black people in the school, the white ones correspond to white people in the school, and the gray ones are the others, which could not be people who cannot be classified into either of these groups. And an edge in this network indicates a friendship relationship. So, what you observe here immediately is that there is this existence of homophily, that there are more blacks are more friends with other blacks, whereas whites are more friends with other whites, and there are hardly any connections between blacks and whites. So, this is the idea of homophily that we will build up on from now. So, this is one of the very interesting examples. So, another example was this experiment that was conducted in the San Francisco, where there were 1958 couples who were interviewed. Now, these couples are like they classify themselves into 4 basic classes: the blacks, the whites, the Hispanic or the people from Spanish Portuguese origin, and others who could not be classified into any of these 3. And people from all these origins were interviewed, and the question they were asked was about their sexual partnership. So, given a chance, what type of sexual partner they would prefer, and this particular matrix in the slide shows you like what is their preferences in general, what is the preferences. So, one of the immediate observations from this particular slide, or specifically this particular table, is that the cells that are on the diagonal are the heaviest. So, which again indicates that people who are of the same type are interested to have partners from their same own class, like blacks want to have more partners from the black class itself, Hispanics want to have partners mostly from the Hispanic class itself, white tend to have partners tend to choose partners mostly from the white class, and the others from the other class. So, you see that this is one very typical example in majority of social networks, mostly which are built on this idea of friendship. This particular phenomena is very prevalent. So, the idea is that, again to reiterate, is that there will be, if there are people from the same class, then partnerships or friendships between them is more probable than people from 2 different classes. Okay. So, also this idea could be thought of as like people tend to go with other like people. So, rich people tend to go with rich people. So, you can interpret it in various different forms, but the basic idea is this. Okay. So, some more examples. So, if you now look into the this slide, you see 2 typical examples. The left hand side network, as it shows, is much more assortative than the right hand side network. The right hand side network, on the other hand, is less homophilic, and in general this type of networks are termed as disassociative networks, that is rich do not go with rich usually tend to go with poor. In biological networks, as we have seen long back in one of our introductory lectures, in biological networks you see such disassociative networks. Even in technological networks like router networks, you see this sort of disassociative networks, where like many small computers, many mini computers connect to a large router. Okay, so it's mostly a disassociative network, whereas social networks or friendship networks are mostly associative in nature. That is, popular people tend to go with other popular people, tend to make friendship with other popular people, rich people tend to make friendship with other rich people. That is the basic idea. Now, given this observation from various social networks, one immediate question is like, how can we have a quantitative measure of this particular phenomena? So, now we will see how to quantify associativity. So, the quantification goes like this. So, let us say that there is a node, consider a node of degree k. Now, the associativity can be expressed by a factor called KNN, that is nearest neighbor degree, nearest neighbor degree, and this is defined as the following: k prime p k prime given k, where p k prime given k is nothing but the conditional probability that a degree, that a node of degree k ends up in connecting with another node of degree k prime. So, this is the conditional probability that a node with degree k will connect at its other end with a node of degree k prime. So, this conditional probability multiplied by the node degree at the other end, the k prime, sum of this over all nodes or all such k primes defines the nearest neighbor degree. So, the idea is very simple. So, what you do is, let us say that we have a node x. Now, we look at the degree of the node x. We also look at the degree of each of the neighbors of x. So, let us draw it like this. So, suppose you have a node x here. Now, say x has k neighbors, n1, n2, n3 up until such k neighbors, and then what we do is we see what is the degree of each of the individual neighbors. We check the degree of each of the individual neighbors. We find an average of the degree of the neighbors, that is the nearest neighbor degree. So, we find an average of the degree of all the neighbors. So, that average degree, so you have the degree of the node x and the average degree of the neighbors. So, you have these two things. On the x axis you have the degree of the node x, and on the y axis you have the average degree of the neighbors of x. Okay. Now, if this plot is a scatter diagram which mostly concentrates on the y equals x line, then you have a high probability that nodes with similar degree or nodes of similar degree are friends in a social network. Okay. So, what you see is that my degree, which is k, is highly related with the average degree of my neighbors, right. So, that is the idea. So, if my degree is highly correlated with the degree of my neighbors, then it is a assortative network, and such correlation is reflected by the scatter diagram, which is concentrated close to the y equals x line on this particular plot. So, this is how you basically identify by plotting the degree and the degree of a node and the average degree of the neighbors of that node, by plotting them on the x and the y axis and looking at how well they concentrate around the y equals x axis, you identify whether a particular graph is assortative or not. Now, for instance, if you have a similar plot where you have the k and the average degree of the neighbors of x, okay, k is basically the degree of x. So, and if you have a scatter plot which is just opposite like this, okay, then you have a high chance to believe that this particular network is disassortative in nature. Okay. So, one side, when it is highly correlated, it is assortative in nature. On the other side, if it is highly negatively correlated, then the network is thought to be disassortative. So, just to make things more clear, so look at this diagram. So, in each of this plot, what we have plotted on the x axis is the degree values of all the nodes. So, every node x in the network, okay, we have plotted the degree of every node x in the network, and on the y axis we have plotted the average degree of the neighbors of each such node x in the network. Okay, that generates this plot. And now, looking at this plot and having this fit, having this correlation analysis, you can immediately say whether this is an assortative network or a disassortative network, fine. So, now in order to further nicely quantify this idea, there was this concept of mixing introduced. Now, in order to understand what exactly we mean by mixing in a social network, we will look into the same example that I showed you last time. So, the example of the partnership choices of these 4 categories of inhabitants of San Francisco: black, Hispanic, white and the others. Okay. Now, from this particular table that we see here, we will translate this table into a more normalized version. So, what we will do in this normalized version, each cell of this table, if you look at the slides, each cell of this table is normalized by the sum of all the entries across all the cells of the table. Okay. So, basically you normalize each cell by sum of all the entries in all the cells of this table. So, that means the sum, now the sum of all the individual cells will add up to 1. Okay. That is why we write here, if you look at the slides, that is why we write here sum of ij eij is equal to 1. Now, again from even by looking at this table, you can very nicely observe that the diagonal is heavy. Now, if we have a matrix where the diagonal contains all the values, there is no other values in no other cells, okay, then that would mean that the network is perfectly assortative, that is there is no other value in any other cell except the diagonal. So, blacks only go with blacks, Hispanics only go with Hispanics, others only go with others, and whites only go with whites. So, then in such case only the diagonal will have all the concentration of the values, while the other cells will be empty or 0. Okay. So, in order to quantify this particular notion, we will define the assortative mixing coefficient R, which is basically, so on one extreme you have EII, which is the diagonal element. This is the sum of all the diagonal elements. So you are counting the total density of the diagonal elements by sum of EII. Okay. Now you are subtracting from there the chance that a black chooses a Hispanic or a black chooses some other group with some random chance independently. Okay. So that is quantified by this sum of AI BI, where AI is the sum of the, so as you see here, as we have shown in the table, AI is the sum of the elements on the rows, whereas BI or BJ is the sum of the elements on the columns. Okay. So basically this is independently by chance, if there is a chance that two nodes from two different groups pair up, okay, for sexual partnership. Okay. So that you discount from the total volume. So basically you see what is the actual partnership that you are getting from the data minus the part that you could have observed just by random chance. So this is similar to the idea of defining correlation coefficient, okay, in statistics. So basic idea is, again, if I reiterate, that you have a probability, looking at the data, you have the probability, you can estimate the probability of a set of people, of a pair of people, okay, grouping up for sexual partnership. This is, say, black going with black, white going with white. This value is counted, or this fraction is counted in sum of EII, and from there we remove the part which could be just observed by random chance, which is sum of AIBI. Now this is normalized by, so as I said, perfect assortativity would be when sum of EII will be 1, everything else is 0, that is perfect assortativity. So that extreme is 1, okay, that is the extreme value of EII minus sum of AIBI. Okay. So that is the extreme value of EII minus sum of AIBI. So this fraction is what we call the mixing coefficient. So basically what you see is, you find out what is the probability or what is the chance that blacks go with blacks, white go with whites, and you sum up all these counts minus what is the probability that you see by chance that two people pair up, okay, that is what you discount from this value, and then you normalize this whole metric with 1 minus sum of AIBI, where 1 is the extreme value of EII, that is the maximum that you can achieve. Okay. So if it is a perfectly assortative network, then what will happen, this mixing coefficient again will be, the mixing coefficient will be 1, because in such case you have R is equal to sum of EII minus sum of AIBI by 1 minus AIBI. Now for perfectly assortative networks, sum of EII will be equal to 1, as we said. That implies R will be equal to 1 minus sum of AIBI by 1 minus sum of AIBI, which is equal to 1. So for perfectly assortative graphs, we will have a mixing coefficient equal to 1. However, if it is a disassortative network, then EII will be 0 and we will have a negative mixing coefficient value. So then after this, after we have got a little bit of idea about homophily or assortativity, we will now look into another very interesting concept called Sine graphs. Basically, this is a formal structure of graphs through which you can express, for instance, in a social network or in a friendship network, you can express both friendship as well as enmity. Okay. So, a network by which one can express both friendship and enmity. Fine. So, some of the examples are one that we have given here in the slides. So, look at this graph. So, a plus sign on this network, on an edge of this network would indicate friendship, whereas a minus sign would indicate enmity. Okay. If two nodes are connected by an edge which has a plus sign, then it is a friendship relationship between these two nodes. However, if two nodes are connected by a negative edge, then this relationship is a enmity relationship. And I have this interesting question given our online class. It would be a nice exercise to measure how will it look in terms of this sine graph. Do we really have enemies here? Okay. So, once we have this concept of sine graphs, the first thing that people were interested in studying was this idea of balancing. So, basically this idea borrows from the traditional balancing theory. If you look at these graphs given here, say for instance the first graph, the graph marked as A, you see there are 3 nodes U, V and W. It is a triangle basically. Now, all the edges are marked as plus. So, everybody is a friend of everybody else in this network. Okay. So, this is a very stable configuration. Now, let us take the second example. The second example is a bit tricky. So, what you have here, that there are 2 nodes who are friend among each other, and both of them actually share an enmity relationship with the third node. Okay. So, this is again a possible configuration, because 2 friends might have a common enemy in general. Okay. That is also a stable configuration. The third one is where you have at least 2 edges which are positive, whereas the third edge between these 2 is negative. This is a rare case, and the fourth case is impossible, that there are 3 enemies in a triangle is a completely impossible case. Okay. So, now given these examples of triangles, we can also imagine cases of 4 cycles. Now, like how should be the sine graphs taking 4 nodes together look like? Okay. Some examples are here. So, some of the stable configurations are shown here. So, these are the 2 friends, each of which are enemies, or these are the 2 friends and then there are 2 enemies on the other side. So, these are some of the stable configurations that you observe here. So, in general, the idea is that you should have even number of negative signs in the graph. Unless you have an even number of negative signs in the graph, the configuration is not stable. Okay. Only if you have an even number of negative signs on edges in a graph, then only your configuration is a stable configuration. So, for instance, in this particular example, you see C and D are having uneven number of negative edges. Okay. And that is why these are unstable configurations. Whereas, in this particular case, the 4 cycles you have only even number of negative edges, that is why both of them are stable configurations. So, the next idea that we will talk about is structural holes. So, this is also again a very interesting idea, and we have already looked into some sort of a quantification of this idea in one of our previous lectures when we discussed about betweenness centrality. So, basically structural holes are nothing but nodes or social actors in a network who are like brokers, like they actually transmit information, relevant information from one part of the network to the other part. Okay, they actually behave like information brokers. Okay, so for instance, let us take these examples here. So, structural holes, as it reads out, actually will separate non-redundant sources of information. Okay, sources that are additive and not overlapping. So, basically if you have two parts of the network, say one here and the other here, so basically this green node here is denoted as a structural hole, because we are imagining that the information that is there within this particular group of members in the social network is very different from the information that is stored here in this group of networks. So, that is why we call this particular node a structural hole. So, we have a word of caution here. There are two things that one needs to be careful about. So, a cohesive group cannot have a structural hole. For instance, if you have a network like this, so this is a very cohesive network. And since this is a very cohesive network, everybody has similar piece of information. That is why nobody in this network actually qualifies as a structural hole. Similarly, if there is another similar concept of equivalence. For instance, suppose you have a node here and on two sides of it you have nodes who have equivalent information, then also this is not an example of a structural hole. Okay. So, none of the nodes here, for instance say this node or this node or this node or this node, none of them are structural holes. Here also this particular black node is not a structural hole, because it does not enjoy any extra information more than in either of these green nodes. However, if you have a case where you have a node, same black node here, but then the nodes on the left hand side have a very different set of information from the nodes on the right hand side. Then this particular node actually qualifies as a structural hole. Fine. So, we will stop here.